We are going to do a couple worksheets in 4.1, and they're based on something called confidence intervals. Now, this class has been interesting because, once again, in all of my stats classes, we learned confidence intervals way before we learned hypothesis tests. So, yeah. So, confidence intervals used to be the way that we introduced hypothesis tests. And now we're going to use a hypothesis test to understand confidence intervals. Um, I don't see confidence intervals very often in reports. Hypothesis tests are super common, but confidence intervals not so much. But we're gonna learn them anyway. Uh, I think confidence intervals are easier. They're really similar. It's just kind of two different ways to look at the information. All right, suppose you are tasked with determining if a particular dice is fair. To do this, you are asked to roll the dice a bunch of times to count the number of fives that you roll. Now, this is actually a really bad way to test the dice. Only count the fives. Could a fair dice, or sorry, could an unfair dice reliably give the correct amount of fives? Sure, right? It might give the right amount of fives roughly every time, but it might never roll a one, and it might roll lots of sixes, something like that. But anyway, we're going to do this anyway. So you decide to roll the dice 120 times, and you count up 72 fives. What do you think? This is a fair dice, right? Now, I purposefully made it this far off. So, number one, what percentage of fives did you expect to roll? 16.67. It's 1 out of 6. So 16.16, or sorry, not 16, 67%. What percent did you roll? 72 out of 120 is 60%. Without running a test, does the dice seem to be fair? No, not even close. Okay, so let's set up a hypothesis test. Is this one-tailed or two-tailed? Two, good. What is the null? So H naught is, what variable are we going to use? Pi, because it's a categorical, we're doing a percentage. So pi is equal to 0.1667. And the alternative, HA, is pi is not equal to 0.1667. No. So this makes more sense to you guys, but in the statistical world, they pretty much just stick with decimals. It doesn't matter. It's all the same. If you use decimals on your test, or I don't care. It doesn't matter to me. All right. Should we use simulation or theory? Theory. Why? We have more than 10 successes and more than 10 failures. Okay, and I thought I had that pulled up. Let's see. There it is. All right, so I'm going to run a test of significance. My pi is 1.667, and I want to do one proportion. My sample size is 120, and I could do count or I could do sample p hat. Doesn't matter. My count was 72, and then run that calculation. Oh, I need to change it to not equal to. And let's get this stuff out of the way. And what is my p-value? 0. Look at my z-score. 12. Is there any way a fair dice could roll 72 fives if you rolled 120? Theoretically, it's possible. Would you ever see it in your lifetime? No. A z-score of 12.7 is unbelievably out there. So it's just not going to happen. Okay? So, obviously the dice is unfair. So we're gonna kind of change how we look at this. So number 9, some of you did not do very good explaining or did not explain at all on your tests, which are not graded yet. But this says, isn't it reasonable to or is there evidence to suggest that your dice is fair? Explain. So no. What's our explanation? The p-value is 0, which means we reject the null hypothesis and we accept the alternative hypothesis. And in this case, not only do we reject the null, but we tear it into pieces and we light it on fire and push it off a hill. Well, that'd be kind of cool. Okay. Now, obviously this dice, oh, there should be an is in there, is weighted in some way. Is it reasonable to assume that the long wrong proportion oh boy. I finished this up right before lunch today and didn't have time to read over it. So that's supposed to say long, and I think it copy and pasted on all the others, so they're all going to be wrong. So is it reasonable to assume that the long, oh, that should say run, long, oh boy. Is it Friday? How about run? That the long run proportion for the percentage of 5s rolled with this dice is 48%. Now, this is really interesting. You can pretty much guarantee that that dice is loaded, right? But how do you figure out what the expected number of 5s is? The only way to figure that out is to do a whole bunch of sessions where you roll the dice over and over and over. But even that is not going to be perfect, right? So we know that 16.67 is not true. But what is the true value? And in order to figure that out, we're going to test some other values and see if those are likely. Now, I should probably have put a decimal there. So how are we going to test 48%? I just go back in here. Now, this number is what should happen if the dice is fair, right? Now we're going to put in 0.48, which is just sort of a guess to see how unfair the dice is. So 0.48 is not really the parameter. I don't know what the parameter is. In fact, I will never know. Even if I rolled the dice a billion times, I won't perfectly know how weighted that dice is. I'll have a pretty good idea, but I won't know for sure. Okay, now what? Run the test again, push calculate. And I get a p-value of 0.0085. So if we go back here, what is the answer to 10? No. So do we expect, or is it safe to assume that 48% is an accurate representation of what will happen when you roll this dice and count 5s? No, it's not. Okay, so let's run the test again with 58. So I'm going to run this with 58, and I push calculate. And I get a p-value of 65%. So if I came to you and said, hey, this dice is unfair, I think that this dice will roll 5 58% of the time. What are you going to say? Sounds reasonable, right? If the null hypothesis said 58% and you get a p-value of 0.65, are you going to accept the null or reject the null? You're going to accept it. So, are we sure that the true value is 58%? No. But from our sample, we don't have evidence to suggest that 58 is wrong. Okay? And once again, we'll never know how off the dice really is. But if you told me that you thought the true value was 58%, I would agree, saying, yeah, that sounds reasonable. Okay. So the next question. All right, using the Rossmann theory app, find the highest percentage of 5s that would still result in us accepting the null hypothesis. I think let's just do a percentage with no decimal. I mean, it doesn't really matter, right? Yeah, you could. So let's just stick with whole percentages. That'll make it easier. So how are we going to do that? So I'm going to keep changing this to, let's try 99. And then run the calculation. So, do I think, why is it negative? It's gone all the way around the world and then come back. But it should be positive, right? Oh, because this is, oh, I got you. Because we're changing the pi, we're not changing the p hat. Confused me. So, do we believe that this dice will roll 5s 99% of the time? No. Obviously not right. Okay. All right. So what should we try now? Let's try 68%. No, let's do 60. Let's do 70%. So 70% gives me a p-value of 0.016. So does 70 seem to be accurate? No. It's more accurate than 99 for sure. Okay. So let's change this to 0.69. And I get a p-value of 0.03. Still, I would reject the null. So now let's change it to 0.68, and I avoided this because it's written on your paper. Oh, shoot. It's not? 120, and the count is 72. Okay. Oh, that's going to be a problem. Okay, now our p-value is 6%, which means we accept the null. So it's actually 68 point something, something, something. And like David said, we don't want to sit and focus in on that. Whole percentage is good enough. Okay. So how high could I go? I could go all the way up to 0.68. Oh, that's the answer for 13. No, that's 12. Oh, this should be low, huh? Do I need to redo the calculation in order to answer 13? No. All I have to do is measure the distance from my sample to 0.68, which is 0.08 or 8%, and then go in the other direction. So my sample, p hat, spit out 0.6. And we've determined from 0.6, if we go all the way up to 0.68, we have every reason to believe that the true value could be as high as 0.68. So if I went down the other direction, what would it be? 0.52. Does everybody see that? So anytime you give me a long run proportion, an estimation of what you think the dice is, If that value lands inside that window, we are going to accept the null hypothesis. Does that make sense? Okay. So what do we call the interval included in 0.52 to 0.68? That is called a confidence interval. That's most of its name. Okay? What is that confidence interval based off of? Well, let's name all the things that went inside of it. So what I had to know the null hypothesis. So inside this confidence interval is the assumption that pi is equal to some value that you told me from 0.52 to 0.68. What else went inside that confidence interval? My sample value of 0.6, right? What else went into that confidence interval? The number of people in my, or the number of roles in my sample, 120. Okay? Now, if you change any one of those, it's going to alter the location and width of the confidence interval. But there's one more piece of information that was super, super important. What determined how wide our confidence interval was? What number were we looking for when we ran that test? The p-value of 5%. Okay? If I change that p-value, the size of my confidence interval is going to change. So when we set this up, we were willing to be wrong 5% of the time. So your job in the dice factory is to roll the dice and decide, do I keep the dice or do I throw it away? And you have to decide how willing are you to be wrong. And for this problem, we chose 5%, which means 5% of the time that you roll a dice, or 5% of the time that you throw a dice away, it will have actually been fair. Does that make sense? Now, if you want your dice to be more accurate, you might raise that to 10%. Or sorry, you might lower that to 1% or 0.1%, right? Which means you're going to be throwing away more dice, but the dice you keep are more likely to be fair, okay? So, when we do hypothesis tests, we have to choose what's called the p-value, okay? When we do confidence intervals, we flip that on its head, and we choose what we call the confidence level. So this particular question right here, we have just built what is called a 95% confidence interval. Okay? We have built a 95% confidence interval. Now, understanding what that 95% means is actually really, really hard. Does that mean that I have a 95% chance that the true value is in that window? No. Okay? If I am holding an unfair dice, its true long-run probability exists, and I will never know what it is, right? But if we run a simulation, if we run a sample of 120, so I run a sample, you run a sample, you run a sample, you run a sample. If 100 of us run a sample, then 95 of us will create a confidence interval that captures the true percentage. 5 of us will not. Okay? So what does that mean? Let's say the true value is 0.64. Okay? I run my test, my sample, my 120 rolls. I calculate my p-hat. I build my 95% confidence interval. And I create a confidence interval that looks like this. From 0.50 to 0.67. Did my confidence interval capture the true percentage? Yes, it did. My interval, inside my interval, is the true percentage. So now Malia does one, and she comes up with this. Did she capture the true percentage? Yes. And a whole bunch of people do this. But 1 in 20, 5%, will create an interval that misses the true percent. Yeah. So we cannot use the word probability when we talk about confidence intervals. So once you have your calculations done, your calculation is either right or it's wrong. Okay? And we'll never know if it's right or if it's wrong. But we cannot say our interval has a 95% chance of being correct. Because our interval, if this is your interval, what's the probability that you captured the true value? 100%. If this is your interval, what is the probability that you captured the true value? 0%. Now, if I asked Will, okay, here in a minute, I want you to roll the dice 120 times. What is the probability that his interval will capture the true percent? 95%. Why? It hasn't happened yet. Does that make sense? Yes. Unless you can look into the future. So instead of saying we have a 95% probability that we caught the true percentage, we say we are 95% confident that we caught the true percentage. And I know it just sounds like semantics, probability, confidence, but that's the word we use. We use the word confidence instead of probability. If you haven't taken the survey yet, the process will be right 95% of the time. If you have taken the survey, you're either right or you're wrong, and so we say this is our 95% confidence interval. And then we don't know if we're right or if we're wrong. Okay, does that make sense? We're going to spend a whole nother day working on stuff like this. All right. So what does a confidence interval tell us? So the confidence interval tells us that the process we used to guess the true value will be right 95% of the time. So the process we use to create the confidence interval will be right 95% of the time. And here's a good way to think of that. All right, I shuffle these cards. Okay. What is the probability that the top card is the ace of hearts? No. It's either 0 or 1, right? Because that card exists in position 1 at this moment. And just because you haven't seen it doesn't change the fact that it's either the ace of hearts or it's not. Wouldn't that be cool? Sorry. Okay. Now, if I said I'm about to shuffle the cards, when I'm done shuffling, what is the probability that the top card will be the ace of hearts? 1 in 52. So once the shuffle has finished, then the answer is either yes or it's no. There's no maybe in there. And the same is true of confidence intervals. Before you build it, you have a 95% chance of making a window that will capture the true percentage. But once you've built it, then you can't say probability or chance anymore, which is why we use the word confidence. That's a good question. Okay. And it took me several renditions of this class before I understood that. So I hope that I hope not. Okay, let's find some more mistakes. Your class is hoping to find the percentage of people who prefer cookie dough ice cream over vanilla ice cream. That's not even a contest, right? Cookie dough all the way. This is the top of page 2. Together, you take a survey of 250 people. In your survey, you find that 200 people prefer cookie dough ice cream. So what is your sample percentage? So 200 divided by 25, what is that, 0.8? So our p hat is 0.8. So use the Rossmann Theory app to create a 95% confidence interval for the actual percentage of people who prefer cookie dough. So we're not doing a test here. We have no assumption about what the true value is, right? Nobody said, I think the true value is 75%. We just want to know what is the true value, so we run out, do a survey, we come back with 80%. We need to build an interval around 80% that gives us a 95% confidence of being correct. So I'm going to go in here, and my sample had 250 people in it, not 1,250, 250, and my count was 200. Okay, now what should I do? I need to choose values for pi until I find the biggest or the smallest value that gives me a p-value of 5% or more. So let's guess 82. Do I need to go bigger or smaller? Well, I need a smaller p-value, which means I need to choose bigger. Okay, so instead of 82, let's say 85. So now my p-value is below 5, so I need to backtrack a little bit. So let's do 83. '83 was too far. 84. There we go, 84. Okay, so what is my confidence interval? So the upper end is 0.84. So the lower end would be 0.7. Does 6 not work? Well, okay. Yeah. So this is not the actual way to build it. This is the simple way, right? Nobody uses the Rossmann app to calculate this. So we're just going to go with 0.76. How did I get 0.76? From 0.8 to 0.84 is a 4% difference, 4 percentage points. So I just went back 4 percentage points. And if you look that up, it actually doesn't quite work, but don't worry too much about that. Okay, so this is my confidence interval. So does 83% seem like a reasonable value for the true population percentage in our 95% confidence interval? Yeah. Yeah, so if somebody came to you and said, I believe the true percentage is 83, you do your survey, you get 0.8, are you going to accept or reject the null hypothesis? You would accept and you'd say, hey, 83 sounds good to me. Really what you say is, there's not enough evidence to suggest that 83 is wrong. Okay, so what about 71%? No, do I even need to run the test? No. All I need to know is that 71 does not fit in there. Okay. Now, does it have to be a 95% confidence interval? No, it could be any percentage we want. So let's create an 80% confidence interval. So I'm going to write up here, my 95% confidence interval runs from 76.76 to 0.84. If I lower my confidence, what's going to happen to the width of my interval? The interval is going to get smaller, right? It's going to be wrong more often. 80% is going to be wrong more often than 95%. So to be wrong more often, we're going to narrow the window. So let's go back to our theory situation. And what p-value am I looking for? 20%. So I need to change this, make it smaller, until I get to 20%. Oh, there it is. Okay. So what is my 80% confidence interval? From 77 to 83%. So when somebody tells you a confidence interval, they had better tell you the confidence level. Because I could say something like this. My confidence interval is, I'm pretty sure that the true value is somewhere between 43% to 99%. And my confidence interval, my confidence level is only 10%. Or no, sorry, I did that wrong. This would be, my confidence level is 99.9%. Actually, 99.99. So I have stretched my interval so wide that I'm practically guaranteed to get the answer right. However, how useful is a 99.99% confidence interval? It's just not. Right? There are 46 percentage points between those two. Okay? Or I could zoom in super, super close and I could say, I think the true value is somewhere between 79.9 and 80.1. But my confidence level is only 10%. So it's a balancing act. You have to balance between how willing am I to be wrong and how wide do I want my confidence interval to be. And we sort of just choose 95%, not for any reason other than somebody made a table a really long time ago and they labeled their table 1%, 5%, 10%. And then we just kind of grabbed onto that 5% because it sounded good. Not because it was actually more valuable than any other piece. So it's kind of randomly chosen, but that's what we use. Okay. So I better change this, huh? I'm going to change this to 82. Does 82 seem like a reasonable value for the true population percentage in our 80% confidence interval? Yeah. How about 71? No. Okay. All right. I want you to do 23 and 24. So you can either use your phones or your, you can actually do the rest of the worksheet. So either use your phones or your Chromebook and you're going to answer those. While you're working on that, I'm going to go and start putting answers in because I don't have them all, and I'll leave the answers up on the board. And then you'll know if you're doing it correctly or if I'm doing it correctly. Okay. So with a 98% confidence interval, what p-value are we going to be comparing this to? 2%. With a 25% confidence interval, what p-value are we going to be comparing that to? 75. And you might have to go into decimals to make that one make any sense, but whatever. Okay. Get to work.